Okay, good morning. Yeah, hope everybody's well. Let's get to the second part of the classification chapter. Are there any questions regarding the first chapter, the first two chapters? So decision tree induction and rule-based classification. Okay, then we can get to the next big chapter, the bias classification methods. The Bayesian classification is a statistical classification method. So we are using statistics to try to predict the classes. Mainly we try to find probabilities for each class, and the class with the highest probability is the class we predict. The whole thing is based on Bayes' theorem. We will talk about that in a second. However, we have to, the Bayes theorem, and we will have a formula for that in a second, but it's talking about the probability of an event based on prior knowledge of conditions that might be related to the event. We have one important focus. We are focusing on the naive Bayesian classification. Why are we focusing on the naive Bayesian classification? Well, it's the simplest method to do. And what is naive in this case? Well, we are assuming that all attributes are independent of each other. So we do not have any conditional dependence of attributes on each other. That's a pretty big simplification. Otherwise, it would be much harder to calculate. For Bayesian classification, we have to first define some basic terms. So let's say X is our data sample. So the sample of tuples we are using. This is called evidence in Bayesian classification. All the class labels of the samples should be unknown. And then we have a hypothesis, Ci, that X belongs to a class I. We try to find the so-called posteriori probability P of Ci towards X, that X belongs to this class Ci. So that's the probability that our hypothesis holds towards this data sample X. To determine this posteriori probability, we have to first know three different things. We have to know the prior probability. That is the probability that we are in class Ci. So how likely is it that we are, for example, a female? Then we have to have the likelihood. So the likelihood is the probability that a sample X is within the class. And of course, the probability of a sample data, Px. So how likely is it that we have this sample data we have at hand? That might sound complicated right now, but once we get to an example, again, I hope it gets easy. We have to calculate these three probabilities or likelihoods to then be able to do Bayesian classification. Because if we have these three things, prior probability, likelihood, and the probability of a sample data, well, we do not really need that, but we will get to that, then we can calculate the posteriori probability out of these three things. So we have the likelihood, the probability of a class, divided through probability of a sample. That's Bayes Bayes' theory. Very important, we do not really need the full term in here, the posteriori probability. Since we want to try to maximize the posteriori probability, it's enough to maximize this part of the formula. We do not really need P of X. So we only have to maximize the likelihood times the probability of a class. Why is that important? Because P of X, so, sorry, wrong direction. The probability of a sample data is very hard to get. And that's why we try to skip it and try to maximize just for the upper part of the posteriori probability. Okay. It's again important to say we are doing naive Bayesian classification, so we are assuming that all attributes are conditionally independent. And that's very important to reduce computation costs and also to make it simpler. We can calculate the likelihood, so the first part, in two different terms. For a categorical attribute, we can simply take a look at the number of attributes in CI divided by the number of total attributes in this class. For continuous valued attributes, we have to assume a distribution. Most often you would use the Gaussian distribution for that. And that's why we have this formula down here to determine the likelihood of a certain tuple. In our example, in the lecture, so the example we will get to in a second, we will mainly use the categorical attribute likelihood because it's easier to calculate. In the exercise, we also have a continuous valued attribute to train that. However, it's simply putting in some values into this formula and then we get to our likelihood. We simply need the mean, the standard deviation of our attributes, and then we can simply try to find the likelihoods. I have to admit that it's pretty hard to task you with a continuous valued attribute in the exam, also because calculating this formula in an exam without calculator is pretty much impossible. So do not expect that I will ask you to calculate that. However, of course, I can ask you about the general workings of a continuous valued attribute. Okay, let's go to an example. We again have this big table in here, and that's the same example we had previously with decision tree induction and with rule-based classification. And we want to calculate this time the class of an unknown tuple. So we have a tuple X where we do not know the class by its computer. So how likely is it that X with age below or equal 30, income medium, student yes, credit rating fair, belongs to class Bayes computer no, or to Bayes computer yes? And that's something we can do in naive Bayes classification pretty easily without first training a decision tree or some rules. We simply can use our formulas to calculate that. First, we have to calculate the prior probability of the class. So we have to calculate how likely is it that a tuple belongs to class yes, or how likely it is to belong to class no. We had a complicated formula. No, we not even had a formula for that in here because it's pretty easy to calculate that. It's simply counting how many tuples we have in total and count how many tuples are within each class. In this case, we have 5 no's and 10 yes, if I'm correct, or what's 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 no's. So we have 9/14 is a probability for yes, and 5/14 is a probability for no. Pretty easy to calculate. Everybody should be able to do that, I guess. So not the calculation, but the way to input that into the formula. That's the prior probability. Now we need the likelihoods. The likelihoods are harder to do. We have to do the likelihoods for each combination. And since we know for which tuple we calculate these probabilities, we have to only look at these cases. So age below 30, income medium, student yes, credit rating fair. So we have to take a look at the probability, at the likelihood of age below 30 belonging to the class yes. Of age below 30 belonging to the class no. Of income medium belonging to the class yes. That makes the calculation pretty easy because we only have to take a look at 8 possible combinations, possible likelihoods. For age below 30 and yes, we end up at 2/9. How do we do that? Well, for age below 30 and yes, we simply have to take a look at all the yes tuples in our training data set. So we have 9 yes tuples in here. And now we have to count how many of these are below 30. So we have 1 here, and we have 1 down here. These are the only 2 tuples where we are both of age below 30, or below or equal 30, and of class yes. So we have to set the likelihood at 2/9. For age below 30 and no, what would be the likelihood? What's the likelihood of age below 30 and no? If you follow the same scheme, counting how many age below 30 are within class no. Three over 5, yes, exactly. Since we have the first 2 tuples are below 30 and no, then we have 1 example in the middle in here, and the other 2 no's are not below 30. And we can do the same thing, of course, for all of these tuples. Small side note, we had a little error in these calculations once I uploaded the slides last week. I corrected that error, and the corrected slides are now on Studon. But make sure you have the updated version if you go over these calculations, since I think the example student yes and yes was 5/9 back then. That's of course incorrect. Yeah, but you can calculate these likelihoods pretty easily. Of course, it's some layer, you have to count these things, but it's pretty easy to calculate. These likelihoods are the likelihoods for each attribute. However, it's not the overall likelihood of our big tuple, our data sample. We have to now use these smaller likelihoods to calculate the likelihood of the data sample. That's also pretty easy to do, since we simply have to combine all yes likelihoods and all no likelihoods. So we simply have to use 0.222 times 0.444 times 0.66666 times 0.666666. And that ends up at roughly 0.044. And the same thing has to be done, of course, for no, which ends up at 0.019. By doing that, we now are basically finished, since we only have one calculation to do. We want to find the posteriori probability, or more specifically, the numerator of a posteriori probability. Since it's hard to find out the probability of a sample, we cannot really tell that right now. We have to use the numerator of a posteriori probability. And that's simply using the likelihoods times the probability of a class. For the class yes, this would be 0.044 times 0.643, which ends up at 0.028, and for no, we end up at 0.007. So what is our prediction? To which class do we belong? Most likely for our data sample? A higher or a lower value? Well, it's a likelihood, it's a probability. To the yes class. Yeah, since it's higher, and we want, of course, to predict that we are in the more likely class. Which means our classification result would be, in this case, that X belongs to class C1. While, of course, the mathematical terms are more complicated for Bayesian classification, or naive-based Bayesian classification, than with decision tree induction, I think naive Bayesian classification is far easier to really perform, because it's just taking a look at two different values. We have to calculate these, and then we are finished. However, of course, it's harder to comprehend. In a decision tree, you can easily understand the classification result by taking a look at the decision tree yourself. In naive Bayesian classification, you simply get some weird values, which are not really a probability either, because we still are missing the, we are only using the numerator. But it's easier to do and far, faster. Are there any questions to this point for naive Bayesian classification. I hope the example cleared the most things up. As I said, we can also calculate likelihoods for continuous values. However, that's something we will do in the exercise because it's something we can teach you there far easier. Okay, yeah.
Why is there a power of A in the calculate P?
That's just a footnote. The power of A is just a footnote telling you it's only about the numerator. Yeah, you are right. That's a little bit confusing. It's not power to A. That's just the footnote. Yeah. Okay. Well, then we have one big problem. This Bayesian classification, or specifically naive Bayesian classification in our case, and that's the zero probability problem. Of course, there is a case where some of these probabilities might become zero. For example, if we do not have any example of age below 30 and yes in our class. Then this likelihood would become zero, since we have 0 of 9 in this case. Of course, not in this example, but in a general case. If that would be the case, that one of these likelihoods gets to 0, of course, the overall likelihood would get 0, because 0 times whatever times whatever times whatever is still 0. And if that happens to both classes, or to all classes, all likelihoods would become 0, and therefore all numerators would also become 0, since we are multiplying with 0. And that's a big problem, because then our naive Bayesian classification wouldn't work anymore. We can solve that problem with a pretty easy trick. For our example, let's say we have income low with 0 tuples, medium with 990 tuples, high with 10 tuples. We can use the so-called Laplacian correction, which is simply adding 1 to each case. We add 1 to each case. And therefore, instead of having income low at 0 tuples, we have income low at 1 tuple. We had 1,000 tuples in total. Now we have 1,003 tuples in total, since we added 1 case to each case. And now we are able to calculate the probabilities. Since we add 1 to each case, the most likely case should still be the most likely case, since income medium is still the highest ones of these. Of course, we are not ending up with real probabilities anymore, but we haven't in the first place, since we never got to the posteriori probability whatsoever. So that's a deal we can make to say, hey, we add 1 to each case to avoid the 0 probability problem. And that's something you should, in the real world, always do. In the exam, I might ask for the Laplacian correction. However, if I do not ask for it, don't do it without being told to use it. I will specifically tell you to use the Laplacian correction if there's a task about naive Bayesian classification. That's simply important to avoid confusion. I'm telling you that right now. I will tell you to use Laplacian correction if you are in need to do that. In the real world, please always use it, since it avoids problems. Of course, the lower the amount of training tuples, the higher the distortion is by using that. Since if we only have 10 tuples in the first place, if we add 1 to each case, we might have 5 extra. Then we add 15 tuples suddenly. But with higher numbers, it gets less and less important. Let's summarize Bayesian classification, or more specifically, naive Bayesian classification. Naive Bayes classifiers are very easy to implement, and we obtain very good results for most cases. Of course, for every classification method, there are cases where we do not have the best results. But in most cases, naive Bayesian classifiers have very good results. There are some disadvantages, specifically to the naive Bayesian classifier. One is, of course, the assumption. We are assuming that we have conditional independence of attributes. If we have dependencies, then we are losing accuracy. And in most cases, your attributes will have some dependencies. We will have, in the real world, always some dependencies, some correlation between attributes. And that's something to keep in mind. However, the impact is not as high as you might think if we are not 100% correlated, for example. There are solutions to deal with these dependencies, for example, Bayesian belief networks, but these are not part of KDD. If you're interested in them, you can, for example, find them in our reference book, so the book by Han et al., which was used to build this lecture, and there is there's a whole chapter on that in the book. I even think we are always referencing the 2011 version of the book, since that's the book we have at the library. But in the 4th edition, which was released 2 years ago, there's an even bigger chapter. However, it's not in the library yet, so I'm not referencing that. Okay. That's Bayesian classification. In the exercise and in the submissions, you will be asked to implement decision trees and naive Bayesian classifiers. So the 2 methods we focused the most on in the lecture. And these 2 tasks are also the tasks that are in the pool for the open text question in the exam. So the decision tree induction and naive Bayes classifiers might happen to be one of the 2 open text questions in the exam. I think I mentioned the open text questions. You look confused. Okay, well, then I will summarize again. Maybe I didn't tell you about that. In the exam will be mostly checkbox questions. So questions which are easy to correct, to be honest with you. So we have a fast result, and we have 520 registrations for the exam right now. Even if that's something you might not expect with a room that empty in here, but we have 520 registrations for exam. So most questions will be checkbox questions in the exam. but there will be 1 or 2 open text questions in the exam, and these 1 or 2 open text questions, mostly it will be 2, sometimes it's 1 bigger, but mostly it will be 2, will be derived out of the 6 methods that are also building the submission. So for frequent patterns, it's a priori or AFP growth, which might become one of these, at most 2 tasks. For classification, it's decision tree induction or naive Bayesian classifiers. I will say it, so you heard about it, but I will revise that once we get to clustering. For clustering, it's k-means or dbScan. Those are the most important methods, the methods we are focusing the most on in the lecture and the exercises, and these can become the open text questions. The open text questions have, of course, far more points than a single checkbox question in the exam. However, mostly we have, in the exam, I will aim to get 180 points in total, so 2 points per minute, 90 minutes for the exam, 2 points per minute makes 180 points. You will need 90 of these to pass the exam. The better you get, the better your grade gets, of course. And the open text questions are roughly between 30 and 50 points in this grade scheme. So it's good to be good at them because it's nearly half the points you need to pass the exam, and of course you need a good result in them to be able to get a good grade in the exam. Very important. Okay, that was a rough run through. Of course, we can talk about exam modularities once we get closer to the exam again. But if you have any questions regarding that, we can also talk about that. Okay. So basically, summary, decision tree induction, naive Bayesian classification, very important for the exam. Any questions? Okay. Then we can get to the next chapter of classification, because we talked about classification methods up to now, and we also talked about how good they are. Of course, classification methods are the best if they predict the correct class 100% of times. That's something that most likely will not happen. In most cases, you will not have a 100% correct model. And you will have to have some way to compare different models. If you train multiple models against one training data set, to see which model performs the best. And for that, you need some evaluation. In this chapter, we will compare 2 tasks. One or two different things. We will compare the evaluation metrics. So we will have different metrics to compare models with different focuses. And we will have a talk about evaluation strategies. For example, we need some training data set, but we also need some test data set. So a data set we can validate our results against. And how do we do that? Let's first start with evaluation metrics. We can, of course, take a look at a confusion matrix to do that. In this confusion matrix, we have the classes, the different classes drawn against each other. Specifically, we have the a class and all other classes. So if we want to predict, for example, Bayes computer, like in our example previously, this would be class Bayes computer, and this would be basically any other class. Since we only have one other class, it's class no in this case. So C1 is Bayes computer, not C1 is basically any other class. If we draw this confusion matrix, then if we are predicting Bayes computer yes, and the true class is also Bayes computer yes, then we are a so-called true positive. So we are predicting the correct thing which we want to predict. And it's of that class. The other positive thing is if we are predicting another class and we are really in another class. That's a true negative. That's also a great result for our classification model, since we are predicting the correct thing. That's called a true negative. The two things we want to avoid is to predict Bayes computer yes, while we aren't really Bayes computer yes. That's a false positive. And of course, we can have the other way around, where we predict that we are not of class Bayes computer yes, but we should be when we are false negative. If we have these values, and we can simply use a test data set, run our classificator against this test data set and count how often are we in each class, and fill out that confusion matrix, we can then calculate a lot of different metrics. One very important metric, and arguably the most important metric, is the accuracy. That's the percentage of correctly classified tuples. Correctly classified tuples are basically the tuples out of the true positives and the true negatives. So every tuple which was correctly classified, divided through the total number of tuples, which is positive plus negatives in total, but that's simply the number of total tuples. Another rate which is often used is the error rate, which is basically the inverse of accuracy. So how often are we falsely predicting classes, which is 1 minus the accuracy, since it's the inverse, or basically a false positive plus the false negatives divided through the total tuples. Most often accuracy is used, sometimes error rate is used. There are other metrics. If you are not only interested in how many tuples were correct, how many tuples were incorrect, you can also have different angles of view on your results. Sensitivity and specificity is something you might know from medical tests, specifically the COVID-19 tests. There have been a lot of talks about specificity and sensitivity regarding these tests. Sensitivity is the true positive rate. How often are you predicting a true positive out of the total true class positives? So you are dividing how many of the true positive, really true positive outcomes you're predicting correctly. Why might that be important? Well, especially with a medical test, if you are trying to find coronavirus cases, you try to have a sensitivity of nearly 100%. It's not that important how many false positives, false negatives you have, as long as you have all the positive cases. For example, also with cancer. Rather, you have one or two cases where you predict cancer while you do not really have cancer. That's far less significant than if you would say, yeah, you do not have cancer while you have cancer. It's far more important to have a high true positive rate in that case. And that's what sensitivity is doing. Of course, you can have the other way around, the true negative rate. You do not want to have true negatives, for example, in legal cases. You do not want to accuse someone of murder if they didn't do murder. And that's specificity. Something is negative, it should be negative in our class. So these are more case-dependent measures. Depending on the case, whether it's more important that we really predict the positives or we are really predicting the negatives, then we are using sensitivity or specificity. There are also some more complicated measures. The precision is the so-called measure of exactness. It's comparing how many true positives you have out of all your positives you have predicted. So if you're predicting 100 positives, how many of these have been correct? That's the precision. And the measure of completeness, which is out of how many true positives you predicted correct positives. So either the column of positives or the row of positives. Recall is basically, or it's not basically, it's really sensitivity. That's something you can use as the same word, recall and sensitivity. And then we have some combined measures, the F-beta measure and the F1 measure, which is a measure with a specific beta. So we can have a combination of precision and recall. And the F-beta measure gives beta times more weight to precision. So if you have a high beta, a beta higher than 1, then you are trying to minimize false positives. If you have a beta lower than 1, you're trying to minimize false negatives. And that's simply done by multiplying 1 plus beta to the power of 2 times precision times recall in the numerator. And down here you have beta times precision, since you are giving beta times more weight to precision plus the recall. Of course, the F1 measure is simply the harmonic mean between the two measures. So you are measuring both equally, and you are basically trying to minimize both false positive and false negatives equally. So you do not give more importance to either of them. Of course, we can take a look at an example in here. In this example, we have some true classes: cat, dog, fox, cat, cat, hen, cat, cat, dog, fox. So if we have 10 evaluation runs where we compared a true class we know against the predicted class our classification model has output. And we can use this result to fill in the confusion matrix. For example, for true positives, we simply have to take a look at how often are we really cat once we have predicted cat. That's the case for here and the case for here. And, oh, the case here. So we have 3 times where we predicted true positives. For false negatives, how many of these do we have? One. So we need a prediction of something other than cat, but it should have been cat. So for example, this example is a case. And we have 2 examples of that, where we have dog and cat and fox and cat. It's a little bit easy to oversee some things in here. We can do the same thing for false positives, and we can do the same thing for false negatives. True negatives, sorry. Yeah. And we end up with this confusion matrix. And now we can simply apply the calculations. So for accuracy, we add up 3 plus 4 divided through 10 is 7/10. So our accuracy in this case would be 70%. The error rate would be false positives plus false negatives. So these 2 columns, 1 plus 2, divided through 10 is 30%. Since it's the inverse of accuracy, that seems reasonable. Then we can take a look at the sensitivity. True positives divided through positives is 60%. The specificity is 80%. The precision is 75%. The recall 60%. F1 is 62%. 66%, sorry. 66.6666%, which makes 67%. I've gone through them pretty fast since these are pretty easy calculations. Now we have to talk about how good this model would be. An accuracy of 70% is in most cases not enough for a good model. Of course, with a small example, with only 10 test samples, this might happen. In a real-world example, you would rather aim at something above 80 or even 90% accuracy. Of course, if you compare different models against each other, and your best accuracy you reach is 70%, then it's better than nothing. But predicting only 70% of classes correct is not very good. The error rate is pretty much inverse, so I do not really have to talk about that. Sensitivity and specificity are pretty similar to accuracy. You try to have a very high percentage in here. Which means sensitivity of 60% is not very good. And if we would have had a coronavirus test with 60% sensitivity, I'm pretty sure it wouldn't have been solved. That's not enough. Yeah. In the exam, I often give you something like this upper result set and ask you for calculation of 1 or 2 measures. And I would recommend you to either write down the rates or even to fill out a confusion matrix for yourself so it's easier to calculate. Questions about evaluation matrix? Yeah. So your question was, which one is the most important? Well, it depends a lot on the case. As I said, accuracy is the most often generally used measure, since accuracy is about how accurate is our classifier in total. If we have a classifier where we do not have a specific aim, a specific goal besides predicting the correct class, you would use accuracy. Once you get in cases where it's more important to have one result, correct predicted results, like in medicine, so true positives, you would get to sensitivity, or something like the F1 measure where you weigh, F beta measure where you weigh something in so you have the correct weight. In most cases you would use sensitivity. The F beta measure is not that often used, but it's more mighty to do things because you can have a fine tuning of that. Once you get to cases where it's more important to avoid false negatives, then you would use specificity. It's case dependent. So accuracy is the best measure for general purposes, and other measures are better for special use cases. And you simply have to see which one is, what is more important to you to avoid in your model. In most domains you're working in, there are cases you can rely on. So if you're in medicine, you will have a lot of papers using sensitivity and specificity to do things. If you are in another domain, you might find a lot of papers referring to the F1.5 measure, whatever. Then it might be good to use that measure for yourself. But I wouldn't give them more or less importance than the others. That's why I introduce every of these measures, since they are equally important depending on the use case. Exception, accuracy, and therefore also error rate, since these are the most general purpose cases. Okay, other questions? Then let's get to the next subchapter, evaluation strategies. Well, I already told you that we have to have some test data set. So we have some training data set we are training our model on, and we want to have a test data set which we are using to validate our results. Both data sets have to have true classes attached to them. So we do need to know which classes are we expecting. Otherwise, both cases, both the training and the test, wouldn't work. It's very important that you are not using the same tuples for training and testing. If you do that, you are ending up with so-called overfitting. Yeah, you would receive, you would end up with great accuracy if you have the same training and test data set. But this accuracy would never reflect a real-world use case where you're predicting unknown classes. And I'm emphasizing that a lot since we had a master thesis presentation 3 weeks ago where the student presented the results of their model and had an accuracy of 99%. But she used the same training data set and test data set, which is not good. It's not a result you want to have. It's telling you nothing. You can, throw that classifier to the bin, basically, with these results. Rather, you have to have 2 distinct sets of training and test data sets. And there are some methods to exactly get that, to split a data set into training and test data sets. 2 methods we will introduce are the holdout method and the cross-validation method. And then we will talk about a method to compare classification models and their settings. That's the receiver operating characteristics short ROC curve. Of course, there are many, many more than these, but these are the ones I will introduce in a second. Let's start with a model, a method to split a data set into 2 different methods, 2 different data sets. The holdout method is the simplest of these. We are simply taking a look at an original data set. All of these tuples in this data set have an attached known true class. And we are simply randomly picking an amount for the training data set and an amount for the test data set. The tuples that are hold for the test data set are not used for training. Very important, they are hold back, hold out, to be used later. In most cases, the training set is far bigger than the test data set, and that's okay. A good rough estimate would be, for example, 2/3 for training, 1/3 for testing. You can even get bigger than that in the difference, maybe 20% for test and 80% for training. That's also okay to do. However, you are holding back a certain amount of tuples. It's very important to do it randomly. And not based on time. Since, again, for example, in an online shop environment, you will start maybe by never selling an iPhone 13, and once you get to the later tuples, you sell a lot of iPhone 13s. If you are not sampling randomly in the first tuples and using these, just use the first 2/3 of tuples, you will never have an example of an iPhone 13 in your training sample. And that's something to avoid. You want to have a good mixed through training set, and you will want to have a good mixed through test set. You can vary that holdout method by doing the same thing multiple times. You are using 2/3 for training, 1/3 for testing, train a model on that, validate that model. Then you use the same data set, split it into two different sets, train a new model, and so on. And take the average accuracy over all experiments to validate whether decision tree induction or naive Bayesian classification was the best. More robust than that is the holdout method, is the cross-validation method. The cross-validation method is basically, variation where you have a more stratified approach to the whole thing. You would simply split, we are taking a look especially at k-fold cross-validation. In k-fold cross-validation, you would partition the dataset, the original dataset, into k partitions. So for example, if you have a 5-fold cross-validation, then you would divide your dataset into 5 different partitions of the dataset. And then you would run in 5-fold cross-validation this process of training and validating for 5 times. In the first iteration, you would use the first partition for validation, for testing, and the other 4 partitions for testing. You would end up with an accuracy. Then you would use the first and the third to 5th partition for training and the second for validation, and so on, until you have used every single partition for validation 1 time. And then you would use the accuracy, then you would take a look at the average accuracy over all iterations to validate your model. By doing that, you are using every possible tuple for testing 1 time. However, in each training and validation run, you are still distinct. You are still having a distinction between test and training data. You are not overlapping within each run. And therefore, you do not have any overfitting. I really have to emphasize that. Avoid overfitting by overlapping. K-fold cross-validation is the method which is most often used in training classifiers. That's the method you really read about a lot once you get to classification. And I would recommend you to use that. Then let's get to the receiver operating characteristics curve. This curve visualizes mostly the performance of different classification models. Basically, we are comparing the true positive rate and the false positive rate of a model. In most cases, you can fine-tune the model a little bit. And you can trade off the true positive rate for false positive rate and the other way around. And basically, the ROC curve is about that. You are comparing the trade-off between sensitivity and specificity. Are you predicting more true positives or false positives regarding your settings? A random classifier in most cases would have a very straight trade-off, which is nice, is not nice, which is the worst possible case. The closer you get the curve to get to the upper left corner, the better your model is. And a perfect classifier would have, the purpose shape, but this will not happen. You will likely end up somewhere in between here. The area under that curve, so everything for the random classifier, everything in this lower right corner is the area under the ROC curve, AOC, and that's basically a measure for the model's accuracy. So if you ever shown a ROC curve, the higher, the more to the top left corner your classifier ends up, the better the classifier's accuracy is. And these curves are very often shown, especially with neural network classifiers, but also with some classifiers where you do have settings to do. You will see them very often if you're working with classifiers later on. So it's good to understand them. Yeah, those are the methods we need for model evaluation. Of course, it's a very basic overview, as everything in KDD is. However, it's an important overview. Questions about that? No. Okay. Then we get to the last chapter of classification. We introduced a lot of simple, singular methods for classification. In many cases, it's not enough to have a simple classifier like that. In many cases, you might want to have different classifiers being combined to get a better accuracy, a better sensitivity, a better specificity. Those combinations of different classification models are called ensemble methods. Ensemble methods simply combine different classifiers to get one classification result. And that's what the last chapter is about. Ensemble methods. So we are trying to find a composited model that are combining several models into one composite model. This, in most cases, improves classification accuracy, and mostly the final prediction is made by combining the predictions of all methods. We will take a look at 3 different methods to combine ensemble methods: bagging, boosting, and random forest. We have algorithms for these, especially for boosting. A very popular model within that is AdaBoost. And we have random forest, which is specialized on decision trees. The algorithms themselves are in the appendix. We will not talk about them in detail, but of course they are not in the exam in detail due to the fact that we are not talking about that in detail. The general idea we are talking about can be part of the exam, however, not the code which is shown in the appendix and the details that are shown in the appendix. However, if you're interested in them, you can take a look at these things. Let's start with bagging. Bagging is using the idea of using multiple models to classify the same tuple. Then we have some combinator, the bagged classifier, which is combining the results and simply is using a voting model. So we are collecting the results of maybe 3 classifiers, and then the class with the most votes simply is returned as a final prediction. So basically, we have a tuple T, we put that tuple T into 3 different classifiers. Each of these classifiers creates a prediction. For example, in this case, classifier 1 ends up with yes, classifier 2 with no, classifier 3 with yes. These are then combined into a vote. Since we have 2 times yes and 1 times no, the total result in a majority vote is simply yes. And therefore, the back classifier would output yes. Simple as that. Democracy. Basically, democracy. Of course, you do need some decision mechanism if you have the same amount of votes on different classes, which is a thing you have to decide on once you build a back classifier, but this is not defined for back classifiers in total. For continuous valid attributes, of course, you have to find a way as well. You can still have multiple models predicting the same tuple, and you can still use these results in some way with a vote. Basically, you're using the average of the predictions. So if one has 30 as a result, one has 20 as a result, another one has 0 as a result, then the result in total would be 20 plus 10 plus 0 divided through 3, so 10. That's a back classifier. Pretty easy to do. More complicated is boosting. Boosting is a mechanism where you are trying to learn the classifiers one iteration after each other. And after a classifier is learned, the weights of the training tuples are updated. So the next classifier tries to pay more attention to the misclassified tuples. Let's take a look at that. So we have some original data. This original data is fed into one classifier. The classifier is trained on that original data, and then is tested against the test data set. In the test data set, we might see that some tuples are misclassified. These misclassified tuples are then put into the original data set with a higher weight. For example, by duplicating them or by doing any other weighing process. But we try to put more weight to the misclassified tuples. This weight data is then used to train a second classifier, which is now paying more attention to the new, previously misclassified tuples. And we do that until we get to the last classifier we train. This is now the boosted classifier, where we use all models again to classify the same results. And we are using, again, weighted model where each classifier gets more importance to its votes depending on the accuracy it's receiving. So if classifier 1 has less accuracy than classifier 2, then it has less significance to its vote. In a boosted classifier, we can end up with 2 classifiers predicting yes, while the other one is predicting no, and the result would still be no if the classifier which has predicted no has the highest accuracy. So we are trying to weigh in the accuracy of each tuple, or of each model, which is pretty nice to have. Generally, a boosted classifier should mostly end up with better results than a backed classifier. And I would say in most cases this is the case. But it's more complicated to do. There are more steps to have in mind. Yeah, and for some reason I even completely removed random forest. Okay, when random forest is not on the slides, we will talk about that. You heard about that. I'm not sure why I removed it completely. Yeah. Are there questions about bagging and boosting? Especially boosting, maybe. Bagging is pretty simple to understand. Boosting is not. Okay. When we are finished with the chapter of classification. Classification was a supervised training method where we do have some tuples with known good classes. And we trained different kinds of models on this data to predict the classes of unknown data. We talked about decision tree induction, rule-based classification, and naive Bayesian classification, where I would put the most importance to decision tree induction and naive Bayes classification. Rule-based classification is basically most often done in conjunction with decision tree induction, since we can derive rules from decision trees. That's pretty easy to do. We also talked about evaluation metrics today: accuracy, sensitivity, specificity, position, recall, and the F-beta measure. We talked about holdout and cross-validation, and we also had a quick excursus into ROC curves. And we talked about boosting and bagging in ensemble methods in the last chapter. Next week, we will talk about clustering, which is the unsupervised brother, sister of classification. So we will get to cases where we do not know any classes. Are there any questions about the classification chapter? Okay. Then, a quick reminder. The first submission is currently running. We only have about 100 persons registered for the submission. Only 20 of them have passed yet. So it's pretty important to mention that, since we have 520 registrations for the exam. I would really recommend you to do the submissions. The submissions have people that are doing great in the submissions and are doing a good job in doing the submissions mostly have great results in the exam. That's a big correlation we have seen in the past semesters. So do the submissions. If you are not doing the submissions, we will not have you having better, there is no need to do the submissions, so you will be able to do the exam without that. However, there's a big probability if you do not do the submissions that you will not do great in the exam. So do the submissions. Besides that, we are finished 10 minutes early for the first time, which is great. So have a nice day and have a nice week. See you next week at the same time.